everyone, today we will start the introduction about the pavement design, which is the major objective of this class. In this lecture, we will focus on the introduction about the basic concepts in the flexible pavement design. There are some fundamental concepts for the pavement design. Generally, the pavement design can be categorized into two extreme situations, with the empirical model and the mechanistic model. In the empirical model, the field experiment data will be applied, and we will use the statistical model to find out the material selection and the determination of the pavement thickness. However, this model cannot reveal the impact of the traffic load, climate conditions, and drainage conditions. On the other hand, the mechanistic model have the advantage of analyzing those impacts. However, this model is generally applied for some simple situations, and it will be very complicated for the real-world implementation of the pavement. So right now, most of the design models are based on the empirical model and the mechanistic model, which is the mechanistic empirical model. Currently, in Ontario, the ME model is also applied, and it's linked a little bit to the empirical model. As what we just stated, the empirical design is based on the results of the field experiments or the field observations. It requires a lot of observations to establish the link between the design variables and the performance. Usually we will apply the statistical model to find out this relationship. In that sense, it's not necessary to establish the scientific basis for the observed relationship. There are some typical empirical design models, such as the MTO previous routine design, CBR thickness design, and H2 1993 design, which is commonly applied for North American roads. And this model is also calibrated by MTO, and the MTO 2018 method is generated based on the H2 1993 design, which we will introduce in the rest of this lecture. The ME design will actually combine the advantages of both mechanistics and empirical models. We know that in the pavement design, it's very important for us to identify the distress types with respect to the critical pavement responses. In the ME design, we will use the mechanistic model to determine the pavement response to loadings with some mathematical models. In the other hand, we will use the empirical model to identify the pavement response to the performance of the pavement structure. The combination of the mechanistics and the empirical models can bring some factors to improve the design procedure for the flexible and rigid pavements, including the experimental investigation with the test tracks, the improvements in the pavement analysis procedure, the improvements in the pavement material characterizations, and national and regional pavement performance studies. In the summary, we see that there will be a lot of benefit of introducing the ME design. First of all, the ME design will not only provide the method for us to estimate the thickness of the pavement layers, but also it can provide a comprehensive approach for the pavement design with the consideration of the structure and the materials. In addition, in this design, we can obtain the improved guidance for the pavement rehabilitation design, and we are able to better handle the impact of the climate and improve the reliability of the pavement design. The figure here shows the flowchart of the flexible pavement design. In this figure, the contents in the pink boxes are the input of the ME design, including the traffic loading analysis, climate model, material property analysis, and the pavement structure design. And these input variables will be combined with the drainage conditions and earthwork to analyze the performance of the pavement. In addition, we also need to predict the distress applied to the pavement. If the pavement can provide an appropriate serviceability during the design period, then it's fine for the field construction. Otherwise, we need to go back and modify the pavement structure and repeat the process again until we find out an appropriate pavement structure to support the traffic load in the area during the design period. By summarizing the flowchart, we can then list the components applied for the ME design. First of all, there are a set of input variables for the pavement design, including traffic loading, climate conditions, and pavement materials. We also need to introduce the structure response model to design the pavement structure. After that, we will need to predict the performance of the pavement to analyze the distress applied to the road. Also, the acceptance criterion and design reliability will be applied to check whether the pavement structure is appropriate for the design period and the input variables. Currently, most of the existing pavement design method is based on the AASHTO 1993 method. This method is actually designed based on the extensive AASHTO road test conducted in Ottawa and Illinois. And it will utilize the pavement serviceability for the design. Here, the serviceability is defined as the ability of the pavement to serve its intended function under the existing conditions. In this design method, we have to consider 6 types of information, including traffic loading, subgrade materials, drainage conditions, environmental conditions, pavement serviceability, and pavement materials. All of them have been introduced in the previous lectures. The figure here shows the general procedure of the ME design for the asphalt pavement with the 6 types of information introduced in the previous page. Basically, we need to consider the climate condition, the pavement materials, and also the subgrade materials, and the traffic loading. And they will be applied for the design of the pavement structures. After that, we will introduce the structural response model to analyze the distress applied to the pavement. And the criterion of the acceptance will be utilized for us to check whether the structure is appropriate or not. In this lecture, we will first introduce the Ontario Ministry of Transportation MTO and Municipal Routine Method, which is also called the MTO 1990 method. We also define this method as the granular-based equivalent method, which is a GBE method. The MTO actually has adapted the MTO 1990 method with the AASHTO 1993 method and calibrate the integrated model to generate a new method, MTO 2008 method, and this method has been widely applied for the design of the road in Ontario at the current days. In the routine method, a set of the factors should be considered. The first one is AADT, which is the average annual daily traffic, and the definition of the class of the road. Also, we have to know the properties of the subgrade materials. The drainage conditions and the flow susceptibility of the materials are also considered, but they are considered indirectly. The most important factor we have to consider in this method is the GBE, which is the granular-based equivalency. Usually for the hot mix asphalt, the GBE is set as 2. This indicates that 25 mm of the HMA will be equivalent to 50 mm of the granule base. For the base, the factor is 1. It indicates that 25 mm of the base is 25 mm of the granule base. For the subbase, the GBE value is smaller, usually set as 2/3, and 25 mm of the subbase is equivalent to 25 times 2/3, that is 17 mm of the granule base. And this routine method is widely applied by Ontario municipality, and MTO used this method to make a quick check about the flex of pavements on the road. The table here lists the GBE factors applied for different types of the materials based on the routine method. For the new pavement project, the hot mixed asphalt, including the recycled HMA, will have the GBE factor of 2.0. For the granule base, the value is 1.0, granule subbase is 0.67, and the open grade drainage layer is 1.0. While for the resurfacing project, the GBE factor for all the materials will be reduced. For the old hot mix asphalt, it's 1.25. For the old granule base, it's reduced to 0.75. For the old granule base, it's 0.5. And for the pulverized wrap blended granule, it's 1.0. And CIPR and FDR is 1.8. While for the reconstruction projects, we need to further reduce the GBE factor. For the old hot mix asphalt, the GBE factor is reduced to 1.0. For the old granule base, it's 0.6. For the old granule subbase, it's 0.4. And for the rubberized base concrete, it's usually set as a value higher than 1. This table shows the structural design guideline for the flexible pavement along Kings Highway. In this table, the impact of the drainage and frost has been considered. Basically, in the design, we need to consider two variables: the average annual daily traffic and the subgrade material property. Depending on the AADT, we will have the thickness design for different layers of the pavement structure. Usually for the pavement structure, we have to consider the hot mixed asphalt layer, the base layer, subbase layer, and we need to convert them to the thickness with respect to the GBE factor. For example, if we consider the average daily traffic around 3,000 to 4,000 vehicles per day, and we consider the sand and silty percentage around 60, which means the third column here. Then we need to choose the design guidance in this cell. The thickness of the hot mix asphalt will be 120 to 130 millimeters, and the thickness of the base layer is 150. For the subbase is 600 to 800 millimeters. By using the GBE factor for the hot mix asphalt, it's 2, base is 1, and subbase is 2/3. We can calculate the equivalent thickness as 790 millimeters to 945 millimeters. Actually, with the consideration of the ADT and the subgrade materials, we can specify the thickness at the different locations of this pavement. And this is one example for the design of the Kings Highway, assuming that the ADT is 1500 to 2000 and it's a 2-lane secondary road. The percentage of seal to fine sand is 50. With that, from the table we can find the thickness of the hot mix asphalt layer is 50 millimeters. The granule base is 150, and the granule subbase is 300. In addition, we know that the GBE for HMA is 2.0, granule base is 1.0, and subbase is 2/3. With that, we can find the equivalent thickness as 50 times 2 plus 150 times 1 plus 300 times 2/3, which is 450 millimeters. So that's the way for us to design the pavement structure with the routine methods. Well, most of the values comes from the field experiment and observations. The table here shows the example about the road pavement design in the city of Mississauga. Basically, this design will consider the class of the road and the first serviceability factor. Generally, in this city, the road is categorized into 3 types: arterial or industrial roads with heavy traffic, the collectors which will connect the arterial roads with the residential roads, and it has a median level traffic. The last one is the residential roads, which is inside the communities. The traffic there would be very low. Also, based on the subgrade materials, we need to check the force accessibility for the design. And the force accessibility factor will be categorized as 1, 3, 5, 7, 11, and 15. In this design, we will need to provide the class of the road and the force accessibility factor to identify the thickness of the hot mixed asphalt layer and the granular A base layer. In addition, we can obtain the minimum total road structural depth, which would be the equivalent depth of the pavement structure. For example, if we consider the force accessibility factor of 11 with the maximum of 50% of silt, the thickness of the hot mixed asphalt layer is 100 millimeters, and the granular A base layer is 150 millimeters. The minimum total depth should be 700 millimeters. With that, we can find out the equivalent depth for the HMA layer and the base layer as 100 times 2 plus 150 times 1, that is 350 millimeters. Based on the minimum total depth, we can find the subbase should be 700 minus 350, which is 350 millimeters. So we should have at least 350 millimeters thickness of the base layer. In the city of Misaka, the design of the pavement relies on the values of the force accessibility factor. The figure here shows the way for us to identify the force accessibility factor based on the percentage of the sand, clay, and silt. For example, if we consider the subgrade material with 20% of clay, 60% of silt, and 20% of sand, which is in this case as 20% of clay, 60% of silt, and 20% of sand. By checking the line of these three values, and the intersection could be found at this point, it falls in the region of 50. And this indicates that the force accessibility factor for this subgrade material is 50. You can also check the other values of the sand, clay, and silt to identify the force accessibility factor. And the boundary in this figure is shown as these lines. The corner here is for the value of 1, and the region below this line is 3. The region above is 5, and inside is 7. We also have a region for 11 and region for 15. So that's all about lecture today. Thank you very much for your attention. In this lecture, we introduced some basic concepts about the pavement design. Also, we showed the MTO and the municipal routine method for the design of some freeways and local roads in Ontario. In the next lecture, we will introduce the AI method, the Asphalt Institute method, which will be applied for a lot of pavement design in Ontario.